Okay, now I observe that people did real well on the open math assignment, but the open math assignment is, the stuff they give you gives you a shortcut for getting the right answer, but it doesn't show you why anything works. Now they explain it that it's really easy to bypass the explanation and do what works to get the right answers. Okay. Then if you come into class and I ask you to do these, people have trouble doing it. Okay. Even though you made 100% on the open math assignment, there's something missing. Okay. And people did pretty well with this, once we got a little explanation. But remember last time what I showed you, you break it into a product of two binomials. Okay. And we did that in class. And you got to think in terms of those two binomials, not just find two numbers and multiply out to this and add up to this. Okay, because there's your shortcut. If you don't understand why the shortcut works, you're going to forget it. And you're going to get it wrong. You find two numbers and multiply out to this and add to this, and you can't find them. Okay. And you get confused. So you really got to stick with the principles, okay, which is the distributive law. I think we've been emphasizing a lot in the last week. You really have to understand the distributive law. So what we do is, okay, let's take this x squared minus 8x plus 15. And we want that to equal x plus or minus something and x plus or minus something. Okay. Now, when we apply the distributive law to multiply these two things out, that these two somethings here had better add up to 15. Right? It better have a product of 15. When you multiply this number times this number, right? Okay. So what two numbers could multiply by 15? Well, plus 5 and plus 3 are natural. Now, after you've done a few of these, you know better than use two pluses here when you want to get a minus there, but let's see why. Okay. So you got x plus 5 times x plus 3. Multiply this out by the distributive law, x plus 5 times x plus x plus 5 times 3. Okay. Can you read that okay in the back? Okay. And then that's x times x plus 5 times x. That's x plus 5 times x times x plus 5 times x. And then it's plus x plus 5 times 3. Well, x times 3 is x times 3 plus 5 times 3. Okay. There's your distributive law. And you really have to come back to the distributive law. Otherwise, you do things, forget to put a sign in between these, focus on something besides just using the distributive law. Okay. So you want to write it all out very carefully. And then you've got x squared plus 5x plus 3x plus 15. Looking pretty good. We've got our x squared and we've got our 15. Now, when we do the 5x and the 3x, what we get isn't bad. But 5x and 3x adds up to 8x, not negative 8x. So what we have is a good try. Good try, but we need negative 8x, so we use x squared minus 3. Well, let's do in the same order. X squared minus 5, not x squared minus 5, x minus 5 times x minus 3. And when we do that, you see that we're going to get a negative 5x and a negative 3x. Okay, now little confusion on how you multiply this out using the distributive law. So let's make sure we understand all the details. You got x minus 5 times x minus 3. That equals x minus 5 times x. And then it'll be minus, plus, okay. X minus 5 times x minus 3 can be seen as x minus 5 times x minus x minus 5 times 3. Okay. So we could do minus x minus 5 times negative 3. I said 3 a minute ago. It's times negative 3. So if you do this, that equals, well, this is x squared minus 5x, and we understand that. So I'm not writing out each step of the distributive law, but it's x times x minus 5 times x. Then we got minus, you got to put parentheses around this. We're going to multiply x minus 5 by minus 3, and then we're going to apply the negative sign. Well, x minus 5 times negative 3 is x times negative 3 minus 5 times negative 3. We got to kind of keep our wits about us here. We get x squared minus 5x minus I just did something really complicated. Not times negative 3. The minus here means we're doing x minus 5 times x minus x minus 5 times 3, not minus x to minus 5 times negative 3. So I applied the negative twice. You understand I had a negative here. So only one negative involved. And we multiply this by this. Okay. And then we apply the negative through everything here. We get a negative 3x and a negative of negative 15 is a plus 15. And that's x squared minus 8x plus 16, and that works. That's maybe a little confusing. There are other ways we could write out the distributive law. Probably the easiest way in what I probably should have done it in the first place. And we talked about that. We got x minus 5 times x minus 3 squared. Okay. Now there's a reason I grouped it the way I did here, related to what we did with polynomials earlier. We're doing a binomial times a trinomial. It made sense. Okay. Anyhow, we have x minus 5 times x minus 3. We could write that as x. That's x minus 3 minus 5 times x minus 3. It avoids some of the confusion we have here. That gives us x squared minus 3x minus 5x plus 15 directly. It avoids some of the confusion we have here. Okay. So this is the way I might want to write it out. Okay. Now we move on. We've got x squared plus 2x minus 35. And we're gonna have an X and a something and an X and a something. We make trial and error. We need two numbers that multiply out to -35. Well, we could use 1 and 35, 1 and -35, or -35 and 1, that would give us -35. But the 35 is going to be so big that it's not going to work. And after we've done a few of these, we can kind of look forward and see that. Also, what the open math is telling you, and they tell you why you do this, okay? But again, it's easy to bypass the why and just get to the how, okay? What they tell you is you need two numbers that multiply out to this and add to this, okay? Now, I just start with the idea that whatever numbers we have here have to multiply out to -35, okay? So let's just try two numbers. Let's put a 5 and a 7. And let's just make it x plus 5 times x minus 7. It's not going to be right, but we could easily make that choice. Okay. That then equals x times x minus 7 plus 5 times x minus 7. And we multiply that out and we get x squared minus 7x plus 5x minus 35. Now, two things to remember. Got a negative here, these things have to have opposite signs. If what we have over here is positive, like it was here, we have to have the same signs, either two positives or two negatives. All right, anyhow, we do this, we get x squared minus 2x minus 35. Again, we got a minus 2x, we got a plus 2x, it didn't quite work. But we know we're close, because we got the same number here. This is not quite right. Do x squared do x minus 5 times x plus 7. We get x times x plus 7 minus 5 times x plus 7. That gives us, that's an easy multiplication, gives us this, which is x squared minus 2x minus 35. Okay. Okay, well, that works. And now I want to get into what we call special products. We'll use these two problems to do that. Okay, we got x squared plus 6x plus 9. Now we can put an x with a, we got to have two x's. Now we know it's an x here and an x here because this is an x squared. Okay. If this is a 2x squared, then it gets a little more complicated, and we're going to look at that. Okay. But we have x here and x here. We need a number here and a number here. Multiply out to 9, right? Because we do the distributive law, this is going to end up being multiplied by this. So I'll just try a plus 3 and a plus 3 and see how that works out. Could have used a minus 3 and a minus 3. I could have used a 1 and a 9 or a 9 and a 1. Would have been the same thing, or a -1 and a -9, right? There's all kinds of things I can try. At this time, I'm going to get lucky. This is x times x plus 3. That's 3 times x plus 3. hope you understand these steps. Once you get the 3 and the 3, you're good. If you try a -3 and a -3, that wouldn't really be a good idea because you're starting to get the idea that these numbers are going to add up to this. Okay. I mean, look at what we did here. A 5 and a 3 add up to 8. That's what we got, right? Why did we get 8? Because 5 multiplied by x and 3 multiplied by x give us a 5x and a 3x. It adds up to an 8x. Okay, here, this is going to give us a 3x. This is going to give us a 3x. It's going to give us a 6x. Now, another thing, open math uses that FOIL thing, doesn't it? They use that F word thing. Just yes or no. If they didn't, that's good because I don't like it until you understand what's going on. Okay. But you know that what's going to happen when you multiply these out is this is going to multiply this. Okay. So everything gets multiplied by everything. This is going to multiply this, give you this. This is going to multiply this, give you 3x. This is going to multiply the x and give you 3x. This is going to multiply, give you 9. At this point, when you're learning to factor, well, I'll do that in the next example. Okay. You got x squared plus 6x plus 9 this way. Actually, I'll say it now. So, you know, what you've ultimately done when you've multiplied these out is this is multiplied by this is multiplied by this and this. And I'm discouraged having you do this because it gets awful confusing when you get big polynomials, as we dealt with earlier in the week. In this case, you can look at it this way. See, you have a 3x here, and you're having a 3x here. That's going to give you a 6x, right? You got the 3 times the 3 here. You got the x times the x. It works. And this is really okay when you're factoring trinomials. But still, go ahead and do it using the distributive law. You can look at it like this to verify using the distributive law, simply because I really want you to reinforce the distributive law. That's what's going on. That's the reason this works. Okay. Let's try this. X squared minus 16. Okay, let's try x minus 8 and x plus 2. Not going to work. And maybe you can see why it doesn't work. What are we going to get on x? We're going to get a negative 8x, right? And we're going to get a 2x, which gives us a negative 6x. So once you really understand how the distributive law works, you begin to understand how you can look at this. You can just look at this and see what's going to happen. You're going to get a negative 8x, you're going to get a 2x. You write out the distributive law and see why that happens. And you should do that. But when you get a lot of possibilities, you need to start looking at it like this. Okay. So this isn't going to work. A negative 8x and a plus 2x. I mean, how many x's you got up here? You got 0x, right? There's an x squared, there's minus 16, there's no x, like there was up here. Okay, so that doesn't work. Well, ultimately, you try 4 and 4. One of them's got to be negative, one of them's got to be positive because you got a negative 16. 8 and 2 didn't work. And if you do a plus 8 and a minus 2, it's not going to work just as well. It's going to give you a plus 6x. You got x minus 4 times x plus 4. If you look at it, you got x squared, you've got minus 4x, you've got plus 4x, and minus 16. And I've got it. Okay.
Just the negative.
Yeah. Okay, I'm going to have you try this one. Just now, I'm going to use A, but it's not your A, it's just the symbol A. So I want you to tell me what happens when you multiply x minus A times x plus A. Use the distributive law. A is a symbol, it's not a number. It stands for a number, could stand for your number, but right now it doesn't. Just any old, A can be any old number, okay? So write that out with the distributive law and see what you get. Okay, that was good. You can write this as x times x plus A minus A times x plus A. Okay, so x times A gives you AX, negative A times X gives you negative AX. And A times A is A squared, right? And plus A squared is minus A squared. Minus A times A. Okay. That's just X squared minus A squared. That means anytime you see something like this, where it's a difference of two squares. Now it's pretty easy, you know, everybody pretty well saw this. So it's x minus 4 times x plus 4, okay? It doesn't matter what this number is. For example, I just wrote down x squared minus 81. Well, if you know that x squared minus 16 is x minus 4 times x plus 4, and you recognize that 81 is 9 squared, okay? This is just like this, what we did, okay? There's also an instance of this. If A is equal to 9, that's what we have. Okay, so you've got this formula. Okay, if you understand this, you see that I got the movement wrong here because we had a file that didn't work out. Okay, just like this on this example, sort of, except it's the square of 9 instead of the square of 4, okay? Also because you have this general expression, this general factoring of the difference of two squares. Okay. If A equals 9, then x squared minus 81 is x squared minus a squared. And x squared minus a squared always factors to x minus a times x plus a. We just proved that this and this are always equal. Now we started with this and proved that it equals this. but equality is reflexive. If A is equal to B, then B is equal to A. So if this is equal to this has to be equal to this, right? So here we have a rule. And this is something that's kind of worth memorizing. It doesn't take much memorizing because it's really easy to see. And there's another one. And this is one of your special products. You're going to see it in your home. Another special product. Write this one out. What's x plus a squared? Okay, first thing you need to see if you're squaring this is that this means x plus a times x plus a. It definitely doesn't mean x squared plus a squared. That's wrong. Okay, x plus a times x plus a. You see it's wrong in a minute. You use the distributive law, x times x plus a plus a times x plus a. And that gives you x squared plus ax. Well, actually, write that as xa. Give it an order, plus ax plus a squared. Now, xa and ax are the same. You multiply two numbers, doesn't matter which one's first. You multiply 8 times 7, it's the same as 7 times 8. Okay, x times a is the same as 8 times x. And usually, if x is our variable, we write the coefficient in front. So instead of xa, we want to see ax. Let's see how many x's we got. Okay, so we write it this way. Now, how many ax's do we have here? Show me with your fingers. 2. We don't have any squares out of an ax and an ax. If we multiply them, multiply ax by ax, we'd have a squared x squared. You know you lost the exponents. Okay. Okay, so we have this. And it's not x squared plus a squared. You're used to distributive law, so you want to distribute that squared through here, and it just doesn't work. X squared plus a squared is not the same as x squared plus 2ax plus a squared. That's what it has to be. Okay. And then you start recognizing this product, and open math is going to run you through that. Stick to what you understand about the distributive law. Make sure you understand this in its total context, okay? But these are 2 tricks, okay? It's the difference of 2 squares or the square of a sum. I'm going to write an equation. Okay, here we got x squared minus 8x plus 15 equals 0. How are we going to solve that equation? Well, there is this thing called the quadratic formula. But to understand a little bit more about the quadratic formula before we start using it, we want to, and you know, we'll get to using the quadratic formula, but just a little bit later in the course. Okay, right now, talk about how we can solve this equation because it's easy to solve. If you can factor this. Now, if there's a 14 there, you wouldn't be able to factor. Okay. There'd be solutions, but you wouldn't be able to factor. And you wouldn't be able to find them at this point unless you knew the quadratic formula. And then it's real easy to solve. Okay. But we don't want to get there yet. And if I have a 16 here, you wouldn't be able to solve it at all. There'd be no real number solution. You wouldn't be able to factor it, you wouldn't be able to solve it with a real number. You could solve the complex number, but that's something else we'll get to later. Okay, so point is, you can't always factor this, so you can't always use this method. But if you can factor it, you write this as x squared minus 3, x minus 3 times x minus 5 equals 0, because we've already factored this. We know that's x minus 3 times x minus 5. We're probably tired of the fact that that's x minus 3 times x minus 5, but we're using it because it should be familiar since we did it pretty extensively earlier. Okay, so point is, take this, we factor it. Okay, now let's say that you've got two numbers that multiply to 0. We're going to talk about this trick. Okay, so I asked for two numbers that multiply out to 0. Immediately got 0 times 0. Now we got a little bit stuck on 0 times 0. So okay, that's great. 0 times 0. Is there another pair of numbers that multiplies out to 0? You know, 0 times 0. Well, that's not a bad idea, but it's kind of the same thing. And then finally, somebody said exactly what I wanted to hear. 12 times 0. Well, I'm thinking 12. But yeah, any number times 0 is going to give you 0, right? They don't both have to be 0. Two numbers you multiply, you get 0. Don't both have to be 0. Just one of them has to be 0. Okay, well, what's that tell you about this? Okay, well, I asked what are the two numbers that are being multiplied here, and people want to focus on the x, on the -3 and the -5. The two numbers. Product of x minus 3 and x minus 5, right? So what can you tell me? Oh, this is a number and this is a number. Whatever x is, this is going to be a number and this is going to be a number, right? But one of these has to be 0. So x minus 3 is 0 or x minus 5 is 0. And that's actually very simple. Okay, now just looking at this, just to re-emphasize it. Ask for a number that makes this 0, and I didn't get 12. That was good because if x is 12, you got 12 minus 3, which is 9, and 12 minus 5, which is 7. And 9 times 7 isn't 0. Okay, but people told me pretty quickly, well, if x is 3, that's going to be 0, right? So if x is 3, you're going to get 0 here. Well, that's exactly what the solution to this equation says. And of course, if x is 5, you can see right away that that's going to be 0. Okay. Now, if we plug x equals 3 back into the equation, plug in x equals 3, that would be to this equation, which gives you this. Okay. And that's 9 minus 24 plus 15. And that equals 0. 9 and 15 is 24. 24 minus 24 is 0. Also, if we plug in 5, 5 squared minus 8 times 5 plus 15, And looking 5 there. $25 minus 40 plus 15. That also adds up to 0. Okay. Okay, now 2 things. One, this is exactly what you see in my lab assignments. This is a spring. Okay. And you got to know that that's an ideal spring. Okay, first of all, this actually applies to an ideal spring. You have to recognize that. It's a premise. And that just means the further you pull the spring back, the harder it pulls back on you. It's a fairly familiar thing. A rubber band. Rubber band is not an ideal spring. There's hysteresis and all kinds of stuff involved with rubber band. But for a lot of purposes, including what we're going to do in lab on Friday, you can treat it as an approximate constant restoring force, okay? Or linear restoring force. Okay? It's actually fairly close. Now I want to talk about the graph a little bit. I don't have room to talk about it, so I guess I'll just do what it says. Okay, so you don't have a constant force, so you can't use F net delta X. What F net are you going to use? You're going to use F net when X equals A, which is different than F net when X equals B. Now you be a little closer to an understanding if you said, well, we calculate it for A, calculate for B, and average them. Okay, that would work if A and B aren't too much different. You don't need too much precision. And you do actually, since the force is linear, that actually works. Okay, not going to work here. It doesn't work in general. So if you understand what I'm saying, that since this is a linear force, the average force is the average of the forces at the 2 points. Then you could use F net average times delta S. Okay, and that actually works because that's a linear function. This isn't a linear function. It's just kx to any power or anything but just a straight proportionality. Okay, well. Okay, now you could use this, but we're not even ask you to find the change in kinetic energy, but this could lead to a problem. I could ask, okay, what is the change in kinetic energy? Or if the velocity at this point is this, what's the velocity at this point? Then you have to use the change in kinetic energy, okay? Or you could, calculate the acceleration and integrate acceleration, because you know to integrate acceleration to get the change in velocity. At least you knew that the first week of class, okay? Okay, so we do this now. It's actually stated as F net ds. Okay, S being whatever your position is. Here your position is X. So this is work. This is change in kinetic energy. We just want the work. So we do the integral from A to B of negative kx dx. There's your F net. Your ds is a dx because you're moving along the x-axis. Over here, your ds will be a dr because ours was changed. Okay. And that's just negative 1/2 kx squared evaluated between A and B. And I don't have room to write it down, but it's going to be 1/2 Ka squared minus 1/2 Kb squared. Okay, or 1/2 K times B minus A, A minus B. Okay. So it's 1/2 K times A minus B. A squared minus B squared. But if I write this out, if your calculus doesn't allow you to write this out pretty quickly, then just review a little bit of calculus. This just means you substitute B and then subtract what you get when you substitute A for X. So that's very straightforward. Okay. So that's like how much work that spring force does between X equals A and X equals B. It's the change in the kinetic energy of whatever's on that spring. Okay, as you move from one point to another. And that is, well, we're going to say, because this is coming up Sunday, let me digress and talk about the assignments for a second. Okay, so we talked about how I've extended the time of a couple of assignments. Now, the Sunday assignment is still due when it's due. And the Sunday assignment gets into potential energy. Okay, so I want to talk a little bit about that in the context of this example and this. Okay, this means that if I've got this thing at position B and release it, it's on a spring. It's going to snap back to A, assuming B is bigger than A. Okay. It's going to snap back to position A. So it has the potential to gain that much kinetic energy. This much. Actually, this would assume that A is bigger than B. If A is bigger than B, then it should be positive, so it increases kinetic energy. And you worry about that, but the whole idea is, okay, if I've got this pool ball, I hold it up here above my head and drop it, I'm going to get evidence that because of its position and the gravitational force, it gained kinetic energy. It's cracked into my skull. Not hard enough to do serious harm, but I'm not going to like it. Okay, well, point is, due to its position, gravity can do work on it. And that turns out to be potential energy. Okay, so there's potential to gain kinetic energy because of its position. It's true in a spring. It's true in a number, so an Atwood machine. Okay, you've got an Atwood machine sitting here with two unequal masses. Then it has the potential to gain kinetic energy. If I release it, it'll gain kinetic energy in the direction of whichever mass is greater. So all kinds of things about potential energy. And we've touched on things involving potential energy. That MGH thing kept popping up last time. Okay, that's the gravitational potential energy related to being at a certain height above something else. The pool ball is 1/2 meter above my head. MGH tells you how much kinetic energy is going to be. Because how did we get it? Well, you want to review how we got it, and you want to understand how it was obtained and why it keeps popping up. On the incline, it keeps popping up. Popped up on the curved incline, it popped up on the straight incline. Okay, and we didn't call it potential energy at that point, but I'll start calling that potential energy. We're going to investigate some of that in lab. Just start getting comfortable with the idea of potential energy. So this 1/2 kx negative 1/2 kx squared is related to the potential energy of a spring. We'll be more specific about it when we play around with rubber bands and cards. Okay. Your magnet. When you had the cart close to the magnet and released it, the cart gained kinetic energy. Okay. That was at the expense of potential energy of the magnet system. Magnets were repelling each other. There was a potential to gain kinetic energy, and when we released it, you got that potential. So you've seen that example probably more, and gravity as the two examples that you've had experience with. So you want to start thinking into those terms. The ball at the end of the ramp has potential energy relative to the floor. And when it goes off the ramp, it gains the kinetic energy equal to the loss of potential energy. Okay. The magnet system has potential energy. You release it, it loses its potential energy, but that potential energy goes into the cart. Of course, the cart's on a little bit of an incline, so it's gaining gravitational potential energy. At the same time, it's losing magnetic potential energy. So it gets a little complicated, but when you get the concept in your head, it's not hard to sort out. I mean, there are obviously examples where it really is hard to sort out. But examples we're going to see here are not that difficult to sort out if you get the idea in your head and understand this. Relative to the magnet, and then it'll be relative to this, okay? Well, let's do this. And look at the gas started running there. F net equals negative KX. And if we go from point A to point B, how much work is done by the net force? Well, at point A, here's the force at A. And come down here and we get force at point B. Okay. What's the average force? That's halfway between the force at A and the force at B. Here's the average force, right? We integrate from A to B. Well, the integral is just the area under the curve, or above the curve in this case. That means a negative area. Okay. You know, the calculus, the interpretation of an integral in an area. Okay. It's also equal it's the average force times the length of the integral. Which is the average force times B minus A. It's a formula you had in second semester calculus that nobody ever remembers. And a concept that nobody ever has an idea of because they memorized it as a formula and didn't get the concept. Okay? Not being critical of you, that everybody in the whole universe does that. I don't know why, because it's a simplifying and unifying concept. Okay? So if you don't remember that from calculus, go back and review it and make sure you understand what it is. It's really a very simplifying idea if you're looking at a graph and want to get an idea of how much work is being done. Because if you now have graph of a magnet force, which is a repulsion force, F magnetic, the magnetic force. And you bring to proximity A, you bring the parts of the magnets within proximity A, probably attached to a card or something you're doing in lab. Okay. And of course, if you can do this graph, you took data. You got data. All you got to do is put, 5 or 6 points in a graph, put a smooth curve through it, and you've got a pretty good map of the potential energy of a set of magnets, a pair of magnets, okay? The pair that you measure. You got A here, you got B here. How much work does that do on the carbon? Or what's the potential energy at position A relative to position B? You're going to lose that much potential energy, you're going to gain that much kinetic energy. So the area. Now, you don't have a formula to integrate. Okay. Maybe in a multivariable calculus, we can set up the integral you would do to integrate over all the dipoles. That probably wouldn't be as precise as what you get if you just measure this. Okay. Because that's kind of complicated. But midway through a calculus course, it would be possible to set up that integral and realize that you can't do the integration, so you have to rely on a machine to integrate. Some online. For math. Okay, and there's potential energy A relative to C. If you try to do a quick and dirty approximation, well, there's several things you can do. You take that curve and you can break it. In intervals, like a Riemann sum, right? And on each interval, well, the force is pretty close to constant on each interval. So you just kind of do some kind of approximation like this. So you convert these things to rectangles whose height is pretty much the average height of the curve in that small rectangle. If the rectangles are small enough or thin enough, wherever you put the approximation, it's not going to cause a huge error because there's not much error between the low and the high. So you just kind of put it in the middle. Okay. Now there's Euler approximations. You got a formula. Why use a formula when you can use common sense? Okay. If you don't understand the formula, what do you do? Just sort of use it. Well, yeah, you probably do. Okay. But you don't really see what it's telling you. Okay. Formula for the Euler approximation just makes it obscure to see what's going on here. What's going on here is you're multiplying the average force times the distance. Okay. A force that's not really constant, but it's pretty close to what you get if you use this constant force over this small interval. That's what an integral is. You just take the limit as those rectangles get really thin and you apply squeezing theorems and stuff, and you get the integral. Okay, well, if you want a quick and dirty approximation, you got that magnet, you got that card, you want to see, does this make sense? Can we get a sensible result? The card pick up pretty close to the speed we expect. You just do this. You just try to figure out the rectangle that has the same area as the region under the curve. And what you look at there is this region here has about the same area as this region. This is the region you're leaving out by doing the rectangle. This is the extra that you're getting by doing the rectangle. You can look at it that way. Looks like I might have a little more area here than here, so maybe that line should have been a little higher. Just use common sense. Make a rectangle and see, is that area about equal to the area under the curve? If it isn't, make the rectangle a little higher, a little lower. Adjust it. So that what you're leaving out, what you're gaining by doing the rectangle appear to approximately equal. Probably going to be, for the purposes of, you got to, another thing about the magnet is the force is really weird. It's not a nice force. Okay. It's due to the fact that the magnets occupy a lot of space. It's not a perfect dipole. You don't have what you get. Magnet. We'll deal with that in second semester. You're not going to get into the nature of magnets, except here to they exert a force we can measure. And we can draw a curve. Even if you have the entire multivariable calculus, high skills in multivariable calculus, and high skills with electromagnetism, more than we would expect most students to ever get in the first 2 years of college, okay? Although some could. We will get a nice function here that we can get. So you have to understand these graphs, what these graphs are telling you. And if we put this into Excel and try to fit that curve, you're not going to get it. Okay. I might ask you to do that actually with your data. You're not going to get a good fit to the curve. Okay, anyhow, this is kind of what you're up against and why you need to understand potential force versus position graphs in the relation to potential energy. Allows you to predict what's going to happen, allows you to check and see if everything happens the way happens in a way consistent with the other measurements that you've taken. Okay. So in this case, we do an easy integral. In many cases, you got to use an empirical curve and just do it graphically. Okay. Okay. Now, let's go to this one. Okay, I'm going to ask you to go ahead and tell me what you think is going to happen with this. This is another one of those cases where it comes out nice and easily with really profound implications that really work in the real world. Okay, so again, we're going to go to the item on my summary of mechanics there is this, because we have a variable force. It's a variable force. There we are. And this is the work, and this is the change in kinetic energy. Now, all I asked was for the work, so I'm not even going to address the change in kinetic energy. That comes later. Okay? I mean, you're already dealing with that. But right now, we'll just confine ourselves to calculating the work, because that's. Okay, so what's F net? Well, it's this. And R equals A to R equals B. So R is your variable, so your ds is now dr. And there's our A and B. Very simple. Okay, just identify your variable so that whatever that variable is, that's what your S is going to be. There's more to it than that. That's good for right now. Okay, that's just the mechanics. You get this, and then you do the integrations. Integrating reciprocal of r squared, you get -1 over r. Combined with that negative, you get just a 1 over r, and the GMM is just constant. I didn't specify that that was constant. I kind of talked about it earlier. This is the universal gravitational constant. This is the mass of the planet. This is the mass of the orbiting object. Or in a problem, okay. Let's say we took something, a pool ball. Take that pool ball out 1,000 miles high, or 1,000 miles from the center of the Earth. Let's just say here's the Earth, okay? And here's the x-axis. The Earth is about 8,000 miles in diameter, so we don't go out that far, just go out to about here, okay? But even at that distance, gravity is significantly less than it is at the surface, because we're getting further away. It's like getting further away from the magnet. It's not magnetic, it's gravitational. Gravity doesn't repel anything, magnets can repel, okay? It's not electrostatic, electric charges can attract or repel. Gravity acts a whole lot like electric charges. Okay, so everything we're doing with gravity is going to apply in a few months to electric charges and potential energies and kinetic energies, which is why it's really important to understand gravitation. Electrical charges are just like gravitational objects, except that they can also repel. Okay, so anyhow, here's the Earth. We take this thing out here and we drop it, just like let two magnets come together. Big magnet, really tiny magnet. Tiny magnet accelerates toward the Earth. Okay, how much energy does it gain? Well, there it is. If A is the edge of the atmosphere, wherever that is, okay, because the atmosphere is kind of gradually dissipates. If A is the edge of the atmosphere and B is where we drop it from, then this has relevance for the change in the kinetic energy of that pool ball. It's very, very simple. So that's other details interpreting that. Open my lab will run you through those details, so we can concentrate on the main concepts. Okay. So again, main concept of everything we've done here is the work energy, and specifically the work, but we know that that's going to be related to the energy, and that's the easy part. Once you get the work, if you know the mass, you know something about the initial velocity or the final velocity, you can figure out what's the initial velocity. You know the final, or the final if you know the initial. Okay. And again, we also get, this is a change in potential energy. This is one potential energy. This is the other potential energy. The other thing, we could say that this is potential energy at one point relative to the other. Or we could say that this is the potential energy relative to infinity. Okay, potential energy relative to infinity, you just integrate from A to infinity. Okay. And infinity turns out to be the point at which we want to measure potential energy in gravitation and electrostatics. It's much easier because one of the potential energies is zero to one of infinity. Okay. And want to just mention that, so you kind of at least roll the words around in your head, maybe a little bit of the idea, make it easier when we actually do it. If you were to do a graph of this force versus R, it would look a lot like this graph, but it would have really a different shape. The magnet graph is not going to have a reciprocal square. Okay. Going to have a shape that there's a region in which it does kind of match reciprocal square, kind of matches different power functions as you move out, which is why you can't really do the so numerically. Okay. It's not something that you can find an antiderivative for. You break it into segments and find antiderivatives over segments, but really, you probably don't do that, maybe. Okay, on the prep sheet, AI, which has to be written A with a boldface I, means A, I, vector, unit vector. Okay, so this is really a boldface I, but I can't do a boldface I. Okay. Want to use the arrow. So that's really the only confusion. All we're saying is, if your net force is A times I, your vector force, then I think I'm asking you just to derive equations of motion or something like that. No, actually, the organic. So this for V. Okay, so yes, that would be a 0 D naught, x of 0 is x naught. So that's just a derivation that we did the first week. We did it with omegas and thetas and alphas, okay? But no, we connected it. But we started with rotation because we could observe it in detail. See, clearly see a little bit of nonlinearity. Okay, that's one of the questions. Okay, so there's a question about the projectile problem. Let's take some sorting out. And how do you identify what the main principle is? What is the main principle? Not what habit do you follow, which is to do your x equations and your y equations. And it's a good habit. It's directly related to the principle. What's the principle? Okay, so again, we're given Vx, Vy in the altitude at a given, at some instant. I can tell you what the time is. That's what we're going to figure out. Okay, because we can twist these around any way we want to. Okay. There's enough information here that you can answer the question if you're also given the initial altitude, when did it start? Okay, all you have to do is those equations. So that would be your reflex. But if that isn't your reflex, what's the main principle? Okay, the main principle is, in this instance, we have the x and the y equations of motion. It's uniformly accelerated, or integrals if it isn't. Okay, the basic principle. Motion in two more dimensions. F x and y and f z are linearly independent, meaning that none of these, that the forces in none of these directions have any direct influence on the forces in the other directions. It, of course, means then that your force is a vector quantity. The basis is ijk. Okay, now that's putting it into more sophisticated language than is required for this course. but that just means that these things act independent. Okay. It's good if you have linear algebra to put it in the context and just put it in. The majority of the things has, but it's certainly not something that you're going to have to do in this course. It's something that can be useful to reinforce the concepts that you developed in that course. But, okay, so I use this language. It just means, again, independent. Did I use words literally independent on the sheet?
You did.
Yeah. Okay. Well, again, if you don't know what that means, I just told you what it means. They don't influence each other. Okay. And I'll just say independent. So if these are independent, assuming you have a constant mass, these are independent. And if these are independent, these are just integrals of these, so they're independent. And these are just integrals of these, they're independent. Okay, which means now you can do what we always do with projectiles. There's a deep principle there, though. It's the forces in perpendicular directions don't directly influence one another, or the motion in those directions. Okay. So that's motion. What do we know? We know Vx. Okay. That's given. We know that Ax equals 0. So V of P equals Vx. So now we know the velocity function. And we know then that X of P equals Vxp plus X naught. The horizontal motion of an ideal projectile is always that simple. Now, depending on what we're given, we might not be given Vx, we might be given T, we might be given A. Oh, we're given A, it's 0. Okay. So we always get that in the y direction. A equals negative G. Always. Okay. A equals negative G, Vy is given, Y is given. Okay. At this point, we can assume a coordinate system and initial velocities. I mean, initial position. We put the initial position in where we want to. And where we're going to put it here is we're not going to put it at the time when it started. Okay, we're going to put it right at this time. So that Let's say H is given here, not Y. Okay. So let the origin be is a given point. Not equals 1, not equals 0. So now it's easy to plug things in and find Vx and Vy of t. We've already got Vx of t. X not 0, it's just Vx times t. Now that applies to negative times 2 because we can go backwards in time because this was moving, from the time it was at height, what we call it, initial altitude, whatever we call that. Okay, I think I just gave you a number, right? What are your numbers like? F or something. I don't want to go into detail on how to solve this. I want you to work it out. Think it through. Here's what you do. That's kind of what you always do. Choose your coordinate system. A coordinate system is always vertical, horizontal for an ideal projectile. Because you want one of the dimensions to have all the acceleration. Otherwise, it can be done, but it's a lot more complicated. So again, the note I'll make, H is given. What is H was your G. And what was initial height was here. Okay. So H is your G number, which is greater than your D number. Initial altitude was D, and these are in meters, right? So it's got to determine what Y equals D minus G. You can do this graphically. Here's your coordinate system. And here you are with the Vx and the Vy. I don't know which rising you're following. But I think I gave you a positive Vy. I don't know. I could give you a positive thing. It's better. You plug it into your equation and stuff. You want to get this. So right now the velocity is here. And your altitude relative to the ground, let's say, is G. Here again, that started at some other time. So you got this parabola. And here is D. This height is where you start. This part of the curve isn't relevant. So now you got this parabola. You have enough information to determine the equation. So one way or another, you got to find D when y equals g minus 2. G minus 2. So at this point, that's very well drawn. There's your mental condition. And it's coming down. Already hit its peak. Sure, maybe it has. Okay. There's a picture that shows you what your target is. It's the time of this curve. Okay. Now on the major quiz, I'm probably not going to give you I don't remember what I put on there. Thinking through a lot of problems in the last couple days. So I boiled it down. So I'm not sure what I asked you for projectile, but it doesn't really matter. This is how you set it up. Here's your premise. This allows you to set up the X and Y independently. You plug in your information. You have enough information. You solve it. And remember in class, we solved the hardest, what I think is the hardest problem, which is when you know where it landed and the angle at which it is projected. Figure out everything else. Okay. And that's what you got to do for lab anyway. If you can do that one, you pretty much do any of them, especially if you happen to remember to divide by 2 at the end, like I did. Remember, we went through a lot of, somebody set it up with tangents. You just use sines and cosines. There are advantages of both. Doesn't matter how you do it, as long as you keep your wits about you and do the algebra, which is not simple. Okay. Did I tell you what happened with that video? How many people do you think watched that video? More than 10? 650. So they all really loved that video and watched it in an incessant loop for weeks. But this all happened within a couple of days. Okay. So somebody out there picked up that video, recommended it, either so they could laugh at me for not dividing by 2, or because there's some information they thought was there. Most people didn't watch much of it. They watched, a minute of it, 30 seconds of it, and said, I don't want to do that. Or that guy doesn't know what he's talking about. Is that right? Okay. I don't know why that happened. And then nobody's really watching much since. I haven't checked it in the last couple of days, And it's a mystery to me how that happened. But whatever the reason, I hope it did somebody some good. It also got 7 likes. That's more than a 1% like percentage. And that's actually pretty good for a physics video. Nobody really likes it. So some people apparently got something out of it. Even that, they got a good laugh out of it, not divided by 2 at the end. Okay.